last class. It's much better up for this class. Okay, let's take a look at question 11. And so I'm guessing that the issue is doing the actual calculation. But let's set this up because it'll give us a chance to make sure that we remember how to do, because on the quiz I just say, do the surface area. What's the formula? Oh, it's not that hard. Here, let me remind you the formula. The formula is this. Surface area is the integral of the surface area of a cylinder. Remember the surface area of a cylinder? It's 2 pi RH, 2 pi RH. So 2 pi R times, not H though, we have to slightly change because this isn't a cylinder. It's tilted in or out, you know, it's a weird shape. So it's 2 pi R times the arc length, 1 plus the derivative squared. So that's what we're going to use. By the way, arc length, just to remind you, because actually this is on the quiz too, because I thought we might as well review arc length. I don't think we actually had a quiz on arc length. That's easy. It's just that part, the radical part, 1 plus the derivative squared. So, so there's the arc length, and you can see why I keep saying that you're just taking that arc length and sticking it in there for the surface area. Anyway, getting back to this, let's set this one up. So I'm doing this, and this is around the x-axis. Yes, thankfully. Up here, you had to do both the x and y-axis, but here it's all just around the x-axis. So I've got my curve, the cosine of 1/2 x. Just a minute. That means that this is going to be, hold on a sec, stretched out, 1/2 x. Okay, so this here is pi. Had to think about what this looked like. So we're rotating this around the x-axis. You'll end up with a shape that's sort of like a bullet, or the tip of a bullet, I guess. You know, it'd be like if you can imagine what it's going to look like. Sort of a cone that kind of comes to a point. Maybe that's a better way of putting it. But anyway, so that's what we're talking about. We're rotating around the x-axis. If I want to put a representative rectangle, that's where it would go. And so that helps me figure out what R is. R is this. So let's see, this is going to be the integral from 0 to pi of, I'm going to put my 2 pi out front, if that's okay. R is the cosine of 1/2 x. And then in here, I'm going to have 1 plus the derivative of cosine 1/2 x. So that will be 1/2 times the sine. So this will be the sine of 1/2 x. Before you go bonkers, let me just write out what I've got. Just a minute, that doesn't look good. And that line is bothering me. Just a minute, I need to move this stuff over. That line is in my way. There we go. Okay, just a minute before you lose your minds. There we go. Okay, dx. Okay, so f prime, I will write, sorry, that line is really bothersome to me. Okay, so f prime, in this case, is negative 1/2 times the sine of 1/2 x. So hopefully that's not a problem. I mean, you can do that yourselves. And then when I square that, if I take that thing and I square it, of course, you get 1/4, positive 1/4, because negative squared is positive. 1/2 squared is 1/4, and then, of course, sine squared. So that's where that stuff came from. So far, so good? Looking good. Okay, so if you've got this, you're most of the way there. The main thing is finding that final integral, but I'm glad we had at least one where we got it all set up. If we need to set up any of the others, we can do that. But let's go ahead. I'm gonna, this stuff is gonna bother me, so I'm gonna copy this and go down here to a place where it's blank. Come on, come on. There we go, that's blank, there it is. Okay, so let's actually do this. I know it looks scary, but it's not as bad as it looks. What we're gonna do is we're gonna do a basic substitution here. So bear with me. My u is gonna be the stuff under the radical. So 1 plus sine squared. Oh, wait a minute. I got ahead of myself. I thought that that's what my u was going to be. Drat. Oh, this is not happy. Okay, u is going to be, I'll do it. I got myself into this. So not sine squared. Let's do sine 1/2 x du. You know what? I'm going to do du equals this for reasons that will be more apparent in a bit. Just a minute. Sorry, I keep changing. Over 2. So that's going to be my u. Yeah, I've suddenly become sad. So Hunter, you're keeping me honest or making sure that I do my job. So thank you. So this is going to be 1/4 times the cosine of 1/2 x dx. I don't know why I put double parentheses there. Let's get rid of one of those sets. We don't need that. So let's pause for a minute and make sure, now that I see what I'm getting myself into, take a deep breath. It's going to be okay. That look okay? Okay. So if we're happy with that, now we're going to, what are we going to do? Oh, yeah. We're going to do this substitution. Give me a minute here while I get this set up. This is 2 pi integral of 0 to pi of the radical of 1 plus sine of 1/2 x over 2 quantity squared times cosine of 1/2 x. I keep putting extra parentheses times dx. I need the 1/4, so I'll put that there, but I'll put a 4 out front. So far, okay? Yes, this is my penance for choosing this. Okay, so let's go ahead and make this substitution. You can see here is my du, and I've got u right there, so this becomes 8 pi, come on, buddy, 8 pi times the integral of the square root of 1 plus u squared du. I feel like this is one of the standard antiderivatives that if I actually had brought my book, it might be in the front inside cover or back inside cover of the book, but I can't remember it offhand, so I'm going to have to suffer a little bit more, but not too much more, don't worry. And that is, I'm going to do this. I know it feels like you're going from trig functions to u and then back to trig functions. Sorry. It's the only way I can think of to do it, so that's the way we're going to do it. So we've got a u here, we've got a 1 here, and you've got this, 1 plus u squared. Oh, joy. And so let's see, the tangent of theta is equal to u. The secant of theta is this radical. And then du is going to be secant squared. Just keeps getting better, doesn't it? Because now we have secant cubed. Not at all happy. And so we dealt with this one before, didn't we? So I feel like I've already done this one, and I don't want to take up any more time to do it. So my apologies. This one makes me sad. But I'm just going to cheat, if you don't mind, and use my computer to do this one. And then we will go on. I will make sure, I'm almost 100% sure that the one on the quiz, you're not going to have to mess with this. So let's see. Let's just integrate just a sec. You could do this in Python, or I'm just using another program here. So let's see. We'll do the secant cubed with respect to x. And I got, let's see, this is 1/2. Interesting. Okay, yeah, this is, we had done this before. So this is 8 pi times the tangent times the secant over 2. I guess I have to put this whole thing over 2. You remember we did this, it was the one that I accidentally put on your test, secant tangent. So it looks somewhat familiar. I don't know if it does to you, but it looks to me that's familiar. Now we can go back and I guess let's finish it up. So we have 8 pi over 2, I don't know why I did that, times x times the square root, oh, it's not x, it's u. Give me a sec here. Now I just want to get it over with. U, 1 plus u squared, times plus natural log of square root of 1 plus u squared plus u. Okay. And then we have to go all the way back here and say, what is u? U is this. Okay. So 8 pi over, just write that as 4 pi. 4 pi times, where was it? Y. Okay. Sine 1/2 x over 2 times 1 plus sine squared. This is so ugly. Okay, you get the picture. 1 plus sine squared 1/2 x over 2. Sorry, that 1 isn't over 2. Oh, it's over 4. 1 plus. Yeah, you can see I've really lost my interest in doing this one. Whatever. And then we have to plug in the limits. Limits are 0 and pi, aren't they? Let me see, can I do that? Yeah, I can. Oh, yeah. No, actually 0 and pi. Won't that be 0? Yeah, this doesn't make any sense to me. So I'm going to just leave it for now. 0, because it's 0 to pi, isn't it? Oh, pi over 2. Okay, maybe it's okay. Sorry. 0 to pi. So this will be 4 pi times 1 plus square root of 5/4 plus ln of square root of 5/4 plus 1/2. Okay, I'm going to go with this. I don't know if that's, this should be over 2. Yeah, whatever. I'm still not thrilled. I don't think that's right. But I want to move on. So sorry about that, Hunter. I think I just picked, I thought, oh, it's sines. Can't be that hard. I need to remember, it can be. Anytime you have, I mean, it's just such a simple cosine of 1/2 x. What's so hard about that? Well, we just found out. Okay, so let's go back. Maybe we could do one that's more happy. Is there anything else that we can do, either from here or from here? The one on your quiz, just to warn you, I'll even tell you what the quiz has on it. It has 2 problems that are the same curve, but one is do the length of the curve. So that's this formula, length. And then the other one is do the surface area of the curve, which is that formula. So the length you can do by hand. You can actually do it. It's not a hard one. But when you get to the surface area, I think you might be able to do it by hand, but you use your calculator. Okay, so anything else from this that we need to do, or should we just get it over, do the quiz? I see people are just like, no, let's get it over with. Let's do the quiz. Okay, let me give you the quiz then. Find this, 1, 2, 3. There you go. There you go. Enjoy. Here's 3. That might be 3. If that's not, I'll make sure you get enough. Is there enough? Here's one more. There you go. That's only 2. Thomas wants. Yeah. There's a bunch in the drawer up there. And if you can't find that one that works, mine works up front. So nice. 1, 2, 3, 4. Is that 3? I think that's 3. I think that's 4. Yeah, everyone's here, so I've got just enough. Does that thing work for you? Or do you want this one? You want this one. This one for sure works. Oh, press on. Yeah. Oh, this one does work. All right, did everyone get one? Who wants one? I'm just kidding. You all want one. All right, I'll see if I can find my copy. Okay. Yeah, I just realized that on the first one with the length, even though you can do it all by hand, it's kind of helpful to, because the numbers are big, to use your calculator to compute like 37 times whatever number you have to multiply it by. It's, you don't have to do it all by hand, is what I'm saying. Yeah. 30. Let's do this. So I noticed some of you are done. Some of you are still working this fine, but I have something that we're going to be using a little bit later that I'll give you just so that you, if you're bored, I think it's pretty self-explanatory. It's like a little puzzle that you probably remember from when you were a kid or maybe in middle school having to do puzzles like this. So if you get bored, you can do these puzzles. It says quiz, it's not a quiz. It's just, I used my template for quizzes to make this little half sheet of paper. There you go. Down there. There's that. Oh, there you are. Enjoy. Whoops. Oh, I got it. It's close again. Yeah, there's yours. There's two. There's two more. Enjoy. Hope I've got enough. I do. Here you go. Enjoy. Make sure I got the right one. Just a sec. Okay, so I'll tell you what, on the first, I don't want you to spend too much time on this quiz. On the first one, if you're stuck, just use your calculator and get her done. And then on the second one, just set it up, use your calculator, get it done. And so the main thing is get that thing set up. So if you're stuck on that first one because you're like, how do I do it? It's okay. I'll show you. It's not that hard to do by hand, but I don't want you to dwell on it. So skip it, go to the second one if you're stuck on the first one. Right, so some of you are done. If you are done, I'm not sure who's working on that little half sheet of paper I gave you and who's not. So if you are done, pass your paper over so I can figure out approximately where we are. It's like this front row is good shape here. Like that. Good job. set. All right, thank you. All right, thanks. Sorry. It's all set. Good job. Excellent. Isn't too bad. Good job. All right, set here. Oh, you've got that good. Okay. Nice, nice, nice. Good job. Good job. Well done. All right, you're all set. Or you don't know how to use your calculator? Come on, you did it on your homework. Let me see. What are you doing?
I did it on Monday.
Okay. All right, you're halfway there. Wait, how many parentheses? Let's count them up. 1, 3, close, open, 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 close. So that's that parenthesis. Okay. Okay. So you've got, no, I'm just checking. Okay. So you've got your function,
Right.
and then you put the variable, and then you put the limits. So limits, is that right?
Yeah.
So hopefully, I think I counted your, I think you've got the, yeah, there it is.
Okay.
So that should be, if everything is typed in correctly, then you've got it written down, right? In terms of the, that's that. Okay, good, good.
Yeah.
That's what I want to make sure. Yeah. As long as it's the same as what you have, then that should be, yeah, it's a big number, but you can write it down in scientific notation if you want. Oh, nice. Thank you. So this is all set. Very good. Just polishing things off. Good. Oh, you're just having fun. That's fine. So for the people who are still working on the quiz, this is quiz 15, please just put down an integral, a definite integral, and put down something in terms of the number. Hopefully you've got something that's close, but don't fret if you got an integral. That's the main thing. There we go. Good job. Thank you. Oh, sorry. Trying to keep me from holding it. Let's see. You don't like your integral? No, you don't have to do it by hand. Oh, you get an error.
I couldn't figure out
What?
to calculate a word.
Why do you get an error? Just a minute. You shouldn't get an error. Let me see what you typed in. Oh, you're doing derivative. Yeah, you're supposed to do integral. Let me see. Let me go up here. Let's do math 9. So, let's see. I don't know if you have the right number of parentheses. Let's see if it'll let me. If not, yeah, I don't have enough of the parentheses. Here, just box that up. Because, I mean, if you've got the right integral, then it's just this. So you didn't use a calculator for your homework? You don't like calculators? I don't like calculators myself, but excellent. Any others back here? Oh, nice. That's what we're doing today. How did you know? Okay. Anyone else? Sorry, I can't see with my glasses on, and I can't see them with it on. One over there, good. Okay. All right, so these quizzes are a good learning experience for me and for you, because I realized that if it's interesting to me, it's not a good quiz. So I need to keep that in mind. Oh, I got all the quizzes, right? Okay, yeah. So, no, you got one. Okay, you're holding out on me. All right, I'll come get it. Oh, but you've got an integral though, right? You've got an integral?
Yeah, I got it.
Okay. Oh, you're insistent on doing it by hand now. Okay. Well, if you've got the integral, then I can in my mind figure out whether you did it right. So thanks. Okay. Yeah. You would think I would have learned this by now, but 28 years, not enough apparently. Okay. So let me show you what I have, and then we'll move on. So this first one, which leads into the second one, I guess I thought that it was easy, but maybe it wasn't easy enough, is you do the derivative, of course, Always do the derivative. So there's my derivative. And then I canceled, by the way, if you're curious, I got rid of those. And then I squared this. And so here, I'll do this over here. F prime squared is going to be 9 times 1 plus 2x. So hopefully that doesn't cause you too much trouble. Anyway, well, there's the 9 times 1 plus 2x. So there's my arc length. Arc length, just to remind you, length is the integral from a to b of the square root of 1 plus f prime squared dx. And this bit is part of the surface area formula. So there's the formula. This simplifies, and you get this, which is pretty easy to do the antiderivative for. I didn't write down my substitution, but you could. In fact, you probably should write down the substitution. du is 18 dx. But I didn't bother. Here's what I ended up with as my antiderivative. After doing the substitution, then substituting back. You can see here you're doing the square root of u, so you get 2/3 u to the 3/2. Plug in my limits. So the numbers were big. I just thought it was kind of cool that it came out to be an integer, but being cool is not always the best thing, I guess. So that's that one. And if you have this, here's where I'm happy. There we go. Just that's what I was looking for, is get that. Can you plug this stuff in? Okay, as far as the second one goes, all you really had to do is write down this and the answer. So just to emphasize where everything's coming from, it's 2 pi times the radius, and I didn't draw this surface, but the radius is the function in this case because we're going around the x-axis, times the square root of, so that came directly from up here, the square root of this arc length basically is what you have there. So I just punched that into my calculator after doing a little bit of, and I got this big ugly number. I mean, I don't even know if I plugged it in correctly because some of you have other numbers. Some of you have very different numbers. Does anyone have my number? No, no, no. So that makes me wonder if I punched mine in incorrectly. Wow, such variety. You know, diversity is good, but not always good. Yeah, well, I'll figure it out later. So what are we doing today? I don't know what we're doing today. Let's do something fun and easy. So this is reminiscent of a puzzle game that I remember playing as a kid. And so let me show you this. Wait, where is it? I've got it on here. I've got an online version of this. Give me a sec. Find my thing. There it is. Hold on a minute. Okay. Sorry, it took me a minute. So let's see if this does it for me. Yes, this does it. So this thing, I found this wonderful little puzzle game online that I thought I could play. So let's do the game because the game is much more fun. And let's go to level 4. Level 4 is much more fun than any of the others. So you probably remember doing this as a kid. Is this going to tilt this way? Is it going to be balanced, or is it going to tilt this way? When I was a kid, and literally, this is what we did, is we had something that looked like this, a balance beam with a fulcrum in the middle, and it was marked off just like this, and we have little weights that hung off of it. And so the teacher said, okay, you put this weight here, where do you put this other weight to keep things in balance? Do you remember doing this? Now, I did it with the actual physical thing, physical balance beam, but this is probably more common to what you might have done when you were a kid. And the reason why I figure you must have done this is because you're all smart, and the smart kids are the ones that get to do fun things like this, while all the other kids are learning how to add and subtract. So let's see if we can do this one together. Oh, this one's boring. Is this going to tilt to the left or the right? Is it going to be the, wait a minute, 40, 1, 2, 3, 80, and this is going to be 90. Yeah, to the right, is it not? Yes, I got it right. Okay, so I'll explain why I knew that in a minute. This is the one that I like. So this is similar to what you have on this quiz 16, wherever it ended up, is can you figure out where this goes to make this thing balance? Take a minute, see if you can figure it out. I'll do it up here in my head, and then we will explain how this works, because if you're not sure, don't worry. That's what this lesson is about. So give me a minute here. I've got to do it myself. 30, 90. Wait. 1, 2, 3. Can I move these? I can't move these. Wait a minute. One, two, three. Huh. Well, this is kind of interesting. I can't get it to balance. Am I wrong? Wait, you can get it to balance? $30? Oh, I'm doing my math wrong. I'm sorry. Yeah. Okay, 1, 2, 3, 4, 5, right there. Is that gonna do it? Okay, phew. Sorry. I was adding, I was adding 30 and 30 and getting 90. I don't know why. Okay, yeah, so how does this work? So some of you know, so let's take a peek, and we'll play another one in a minute, because it's kind of fun to get the big smiley face. But how this works is what you're doing is you're computing what's called the moment about the fulcrum for each of these masses. So for example, in this fulcrum, I would compute the moment this way. The moment is equal to the mass times the distance from the fulcrum. So this is what the moment is, capital M for moment. So in this case, the distance here is 3, the distance here is 7, and so the moment on this side of the fulcrum is 7 times 10 plus 3 times 20, which is equal to 130. And for things to balance, you want the moments to balance one another. Now, technically, what we're actually doing is, and probably, maybe I should do this the right way. What we're really doing is this, that these distances are negative. So there, you have a negative 130. And when you do these distances, those will be positive, and this distance will be a positive 10. So when we say that we want this to balance, what we would like is for the moment to be equal to 0 for the whole system. So if it's in balance, it means that the stuff on the right balances the stuff on the left. Or another way of doing it is to think of the entire system and add up all of the moments, thinking of these as negatives back to the left. And then the total should be 0, which puts the fulcrum at the balancing point. The moment, by the way, will tell you approximately, not exactly, we'll have to make an adjustment, but it gives you a hint as to where the balancing point is. And what we'll be doing apparently on Friday is we will be doing centers of mass for objects like this, and so this will give us a hint as to how that works. Okay, so anyway, putting this together, you have the moment on the left, negative 130. The moment on the right is going to be 10x plus 6 times 15 is 90. And so I would like these to add up. So negative 130 plus 10x plus 90 should equal 0. Or you could think of it as that should equal 130. I don't care how you think of it, it's fine. But whatever it is, the way that this is going to shake out is that 10x should equal 40, so x should equal 4 for this to balance on both sides. So for these things to balance. So this is using what's called the moment. Let's go back to the smiley face, because it's always nice to start the day with a happy place. So let's see. We want to know how massive is this potted plant? So let's use moments to figure it out. So to do this, they give you this 15 kilogram mass, and we can plop this down and see what happens. If we put it 1 unit from the middle, nothing happens. If we put it out here at the edge, that's 8 units from the middle, crashes down. So let's see, where can we make this thing balance? That's a little bit, so it must be lighter than 15. Let's try, whoops, let's try here. Ah, that's going to balance. So take a moment and see if you can figure out, this is, by the way, similar to the one that we did on the piece of paper, number 1 from the paper. See if you can figure out how heavy that potted plant is based on this measurement. Just give you a minute here. 30. So you could think of the units, by the way, in one of two ways. I was, since all of these are on these darker units, I'm going to think of this as 1, 2. If you thought of that as 4 units over, whatever, it's still going to work out. But 2 is just a smaller number. So 2 units over, 15 kilograms. The moment here is 30. And then on the left side, you have 3 units over and x units for the mass. So that's 3x. 3x should equal 30, which means x is 10. So there we go. So if you got 10, you're in good shape. Let's see if I can make this little thing go to the 10. Oh, come on. Oh, there it is. Okay. So check. Let me see if the next one's, oh, that's boring. Yeah, whatever. Oh, how much does the tire weigh? Oh, this is funny because watch when we put her on the fulcrum. She sits down. There we go. There it is. So this one's too easy. So I think you can figure out that's going to be 15 kilograms, right? So let's see, 15. That's too easy. So check, yeah, whatever. Well, okay, here's another fun one. So where do we put? So last one that we'll do with this. So where do we put that 20 kilogram mass to make these balance? See, this is, if you can't see in the back, it's 4 kilograms, and that is 1, 2, 3, 4, 5. So I'm going to count these as individual. This is 5 units from the center or the fulcrum. This is 3 units from the fulcrum, and it's 40 kilograms. So where do I need to put the 20 kilogram mass? I'm sure you can figure it out, but I'm going to try to do it in my head while we do this together. All right, so did you get it? Almost? Yeah, is it 7? Is that what I got? Okay, 7 units. So let's do it just to get our smiley face, and we'll go back to what we're doing here. Oh, so happy. Okay, so what's the point of all this? Well, okay, yeah, I guess you can do these for fun. I don't know what the, oh, this one. Okay, so here's the point. So the rest of these are less interesting because they're very similar to what we just did, is where do you put a 15-gram mass to make this balance, and where do you put, yeah, so that's boring. This one, though, is the interesting one. Where should the fulcrum be moved? So let's actually work this out. So in other words, I'm going to take that fulcrum, this triangle here, and I'm going to move it either left or right to get this thing to balance. So, what? Oh, it's on the game. Thank you. Yeah, so there it is, number 4, sorry, number 4. By the way, this reminds me of, I don't know if you're, I don't think that they make them this way anymore, but the old days, the teeter-totters had you could shift not the fulcrum, but the actual board up and down. So you had these like little things that would, I don't know, it was something like this. So you had this, and you had these little, like this underneath. There we go. I think that then there's like a pipe that was there. So you have one kid here and one kid here. There we go. Okay, and then this was like that. But anyway, so back in the old days, the teeter-totters looked like this, and you could actually physically pick the thing up if you had 2 kids, one on each side, and shift the fulcrum, or actually shift the board, so that the fulcrum was either closer to one side or the other. I think they probably got rid of this design because kids were getting their hands crushed in the mechanism there. I'm sure it was dangerous, but back in the 80s and 70s, we were indestructible. But the point is that what would happen is, because I was the fat kid, here, let's see, can I put a fat kid here? There we go. There we go, there's me. What would happen is we would always shift the fulcrum like this, because my mass was always bigger than so the little kid got to go up and down really far, and I was just like the one powering the whole system, apparently. So this guy's yay, and I'm down there. But anyway, getting back to this, we want to know, where should we move that fulcrum? Can we compute, if you can move this left and right, where should we put it so that this thing balances? That's the idea here. And so to figure this out, what we're going to do is we're going to leave the fulcrum where it is and compute the moment the way it is here. So let's see, this is 1, 2, 3, 4, 5. So this I'll just compute the moment of the entire system. So we have -7 times 3. That's the distance of the 3 gram mass, minus 5 times 12. So the 12 gram mass is, 6. Sorry. I just can't count. This is 6 and this is 8. I better double check. 1, 2, 3, 4, 5, 6. Okay. Now I've got it right. So if you were thinking, what the heck is he doing? You're right. I was wrong. Next, we go on the right, and you get plus 8. No, not 8. Plus 6. 6 times 3 plus 9 times 16. I believe I've got everything correct now, but you can yell out if you see anything that is incorrect. I'm going to go ahead and punch this into my calculator because I don't trust my brain for some reason right now. 9 times 16. Let's see, 3 minus 72 minus 24. I guess I did some of that. Uh-oh. Let me try again. 9 times 16, 18, 72, 24. Okay, 66. So I'm getting 66. That's the moment. So I should be very clear. That is the moment. The moment about this fulcrum point. 66, it's positive, which means that the actual balancing point is over here somewhere. Which means that this thing, if I were to just set this up like this, it would tilt down on the right, not on the left. So how do we figure out where the actual balancing point is? Well, the way we do this is think about where the moment came from. The moment, and we're going to do this with calculus, well, on Friday apparently. The moment is equal to the sum of the mass times the distance. So that's what the moment is. You're taking the mass times the distance from the fulcrum. So if we want to know the balancing point is a distance. I have a moment which is mass times distance, essentially. So the units, if you want to do some, what is it called, stoichiometry? You work out the units and all that. That's the only reason I passed all my science classes is I was like, if the units balance, I'm good. So the units here would be like kilogram meters or whatever the units are, gram meters or gram times centimeters. So I want to get rid of the grams. Well, we can do that. Just divide the whole thing, the whole moment. So if I take the moment and divide it by the total mass, that's going to give me the balancing point. So that's going to be the center of mass. So that's on this. Let's actually do this. So the total mass here is 16. Here again, I don't trust myself. 16 plus 3 plus 12 plus 3, and I get 34. So I'm going to take 66 divided by 34 and get not a nice integer, but that's okay, 1.94. 1.94. So what that means is if I were to take this fulcrum and slide it over to right here, 1.94, then this would actually balance perfectly that thing there. So that's what we're going to do. We're going to do this, though, with calculus. So the idea here, just to let you know, sort of a quick preview, we'll do this on Friday, though, but give me a couple of minutes here to do the preview at least. Let's take these two functions, and I know you're getting horrified that I'm going to pull out sines and cosines again, but too bad. And I'm going to graph those two functions. So here's my cosine. Good enough. And here's my sine. Okay. Okay, so notice this region here. So that region, I'll try to draw it a little bit better over here, there, and then there. Okay, that's not the greatest, whatever. Anyway, you can kind of get a picture. It's like this weird looking fish shaped thing. I don't know. It should be symmetric, but it's not, sorry. But I want to know, what is the center of mass of that region? Well, here again, we're going to think about what we just did. We're going to find a moment about what though? So we'll do this. We'll do the moment about the y-axis and the moment about the x-axis. You need a balancing point. Up here, these moments were always the moment about the fulcrum, because that was our point of reference, mass times distance. Down here, we're going to do the moments about the different axes. I'll explain why in a minute. Well, it's because with an object like this, you have a two-dimensional object. To find the balancing point, the place where it'll balance, anyway, we're going to need to know an x and a y coordinate. So we're going to need to know both of those. So we're going to do two calculations. Moment about the x-axis, moment about the y-axis. The moment about the y-axis is going to be the distance, the sum of distance times mass. And the moment about the axis is the sum of distance times mass, just like up above. Now here's the tricky thing about this. If we're doing the moment about the y-axis, I'm measuring the distance from the y-axis. That's terrible. There's the y-axis. So how do I measure distance from the y-axis? What letter do you use? Yes, that's x. X is the distance from the y-axis. So the moment about the y-axis is going to end up equaling the sum of x times the mass. We'll get to the mass on Friday, so that's going to be a bit of a problem, but not a big problem. And then the moment about the x-axis, here's the x-axis, the distance is going to be, the moment about the x-axis is the sum of the y value times the mass. And you can see here that what's going to happen is we're going to take these things, once we can get them formulated well, and right now they're still sort of nebulous, but we'll get a nice formulation for these, is we'll take those and we will do them and make a limit out of them, of course. So we're going to break this up into little rectangles and then add up the rectangles and then turn it into an integral, as is our custom here in this class. So sadly, there's no real homework for Friday. Oh, I was tempted to just give you some to do on your own, because there's also hydrostatic pressure that's kind of fun, but we'll save it. You could look ahead. How about this? You can look ahead, see what it looks like, maybe try the hydrostatic pressure stuff. It's easy. But we'll go over everything on Friday. Have plenty of time. Maybe I'll give you another quiz on Friday that's a lot easier than this one. I'll do my, I'll repent of my hard quiz. Do a good one. Okay.